In this example, we're going to take the method of Lagrange multipliers and apply it to a little application problem. So we want to find the dimensions of the right circular cylinder of maximum volume that can be inscribed inside a sphere of radius 16. All right, so just thinking about the picture here for a second. If you look at a bead like this, a spherical bead, and then they drill a core out, and that core is a cylinder. And so they want to know how can they drill a core that and have that empty space, that core, be of maximum volume. Sort of like an apple core, right? When you take an apple, imagine a spherical apple, and then you cut the core out of it. That's what they're talking about. So our first mission is going to be to draw a kind of picture like that, which is easier said than done. But let's see what we can do here. So we have our 3 dimensions. And to draw a sphere, we'll just kind of draw a circle as best we can. I'm not the best drawer, sorry about that. So that's a sphere if you give it a little waist, right? So there you go. So you take a circle and then you give it a little equator. So there's the sphere, and then what you're doing is you're taking a core out of it. Let me see here. So you're taking this cylindrical core out of that sphere. Right? And that's what we want to think about. All right, now the radius on that core is whatever it might be, but whatever it is, it's actually the same in both of these directions. So your radius is x or your radius is y, but it doesn't matter. So we'll just say radius r. So there's the radius of the lovely little cylinder, and it's the same as the radius over here. Because, of course, it's a right circular cylinder, so it'll be fine. The radius is the same either way. Now the height, well, the height is a little bit tricky. So we want to think about the height is a little bit longer than we might expect. So the height goes all the way from the top to the bottom. That's the height of the cylinder. Okay, so let's keep those things in mind when we think about our objective function and our constraint function. So we want to maximize volume right there. So we can see that that's the objective function right here. So the objective function will be volume. When the volume of a right circular cylinder is pi r squared h. All right, so there's our objective function, no problem. Now we have to think about our constraint, right? Because this cylinder, is nested inside, when this objective function is nested inside a constraint. Now the constraint is that it's inscribed inside this sphere, right? So there's the constraint right there. Now let's talk about that. So let's look at the constraint. We know that it's a sphere, if I could spell sphere correctly, S-P-H, sorry about that, sphere of radius 16, and it's inscribed inside of it. So we know that x squared plus y squared plus z squared equals 16 squared. Right? That's the standard formula for the for a sphere, right, of radius 16. Right, so then we know a couple things. We know that this z right here, let's think about that. If your height is from the top to the bottom, z is actually here. There's a z here and another z here. So that height and that z are related. So 2 z's make a height. In other words, this z is the height divided by 2, right? So if I take the height, divide it in half, I'll have that z. So if I take the height divided by 2 squared, that'll work. And then x squared plus y squared, right? So at this point, we have to remember polar coordinates and various other things, which tell us that when you have x squared plus y squared, that's the equivalent of r squared. We learned that way back in polar coordinates, right? That's the case. If you forget about the sphere for a second and just think about the circle that's in the xy plane, that's what polar coordinates tells us, that x squared plus y squared is equal to r squared. And that will be true even if it's in 3 dimensions, right? So that's the whole polar piece, that x squared plus y squared is r squared. All right, so then we have to make a constraint function out of it because it does us no good in the Lagrange multiplier method if it's equal to a number. So we have to turn this into g of RH, which is r squared plus h squared over 4 minus 16 squared. 16 squared is 256, right? There's our constraint function right here. And for the record, I mean, my volume function, I didn't write it as a function or a function notation, but it's v of r and h. So I'm not actually going to use x and y here. I used x and y only for the constraint piece to figure out how to morph these into r and h. But now that I've done that, I'm not going to go back. So because I'm looking for the radius and the height anyway, I want to find the dimensions. The dimensions that they're asking about here would be r and h, right? The radius and the height of that lovely cylinder. All right, so now let's finally use the Lagrange multiplier method. We know that the Lagrange multiplier tells us that the gradient of f, well actually in this case, the gradient of v, right, because we're using v for our objective function, would be equal to lambda times the gradient of g, our constraint function. Okay, so let's go back up here and look at v. So if I want to take the derivative of that with respect to r, that would be 2 pi rh. Okay, so 2 pi rh. If you want, that's what you're taking v sub r right there. Although my v doesn't look like a v, sorry about that. And then this will be v sub h, the other one, which would be, well, if h is the only variable, then all the rest of this is considered to be a constant, so it would just be pi r squared. All right, that is equal to lambda. And now I need the gradient of this piece, again with r and h. So with respect to r, it'd be 2r. And these two pieces would just be considered to be constants, right? So they don't have derivatives, or their derivatives are 0. So it's 2r, comma, and then 1/4, because there's the 4 there. So it's 1/4 times 2h minus nothing and plus nothing, right? So I can just rewrite that. Sorry. I'm going to write that as h over 2, because that'll just be easier. Right? But if you want to write, it's 1/4 times 2h. Right? That's how we get that. All right, lovely. Okay, so we have h over 2, and then we're going to set these up so that lambda number 1, if you will, is equal to, and I'm going with a number 1 in particular here because I'm going to change it. Give me 1 second. So 2 pi rh is equal to lambda times 2r, right? In other words, lambda is 2 pi rh divided by 2r. And that's also equal to pi r squared divided by h over 2. Like that. So let me simplify this just a touch. I mean, we can see here that the 2's are going to go away, no problem. And this 2 right here is actually going to revert up into the top because it's division by a fraction, so the denominator of that fraction will revert into the numerator because of the reciprocal multiplication property. But then there's another piece that I kind of want to deal with. I want to take out that pi. So lambda 1 is equal to pi times, and then, oh, the r's are going to go away here as well. So that's done. And then it's h. And that's equal to, and then over here it's going to become pi, and then that 2 is going to come up on top, and it'll be 2r squared. So there's the 2 comes from that. The r squared is in the numerator already, and it's divided by h. Actually, I take it back. We don't have to number this number 1. I won't do the little trick I was going to do because we can do this without it. We need to solve this, right? Or at least kind of simplify it. So notice that they both have pi in them, so we can just kind of divide the pi away, right? If you set these two equal to each other, and then I can multiply by h to both sides. And so what will that give me, right? If I divide by pi to both sides, right? Because they both have a pi in it. In other words, we're just going to kind of cancel it out. So the pi's cancel, and then this side ends up being h squared, right? So I'll have h squared over here equals 2r squared. Now, how has that helped me? Well, it helps me a lot because now I can substitute into the constraint. Okay, so my constraint was that r squared plus h over 2 squared is equal to 16 squared, right? Or I could do this and set it equal to 0. Either one, right? It doesn't make any difference. So I'm going to put it back up into this one, actually, just for the sake of convenience. So where it has an r squared, or I could use h over 2 squared, it really doesn't make any difference. I guess I'll just substitute for here. I'll say r squared is h squared over 2. That'll be easier. Okay, so now into my constraint I go. So instead of r squared, I'm going to write h squared over 2 plus, and then it was h over 2 squared, which we said was h squared over 4. So h squared over 4, oh, what the heck, minus 256 equals 0. I'm going to put it back into that one. That way it looks like what we expect. All right, so these two I can combine because I need to make this have the same denominator. So this is a half and this is a fourth. So that makes 3/4, right? So 3, in other words, I'm multiplying by 2 over 2 to get a common denominator. And 2 plus 1 is 3. So it's 3h squared over 4 is equal to 256. So then I need to multiply by 4 and divide by 3. So h squared is 1024 over 3, right? And again, what I did there was I multiplied by 4/3 to both sides. And so therefore h is the square root of that, right? So h is the square root. I don't have to worry about plus or minus because this is a physical object, so there's no way there's negative height. That doesn't quite work. So it's negative 1024 over 3, which is 32 over the square root of 3. And then if I rationalize that, this is fine for me. I'm cool with that. But if you want to rationalize and multiply by the square root of 3 over the square root of 3, it would become 32 square root of 3 divided by 3. And if this was, inches, it would be inches, or millimeters, it would be millimeters, right? We don't know any unit. No unit was given for us. So if we imagine this was, a wooden bead, this might be millimeters, right? Or something like that, because it's a length. So if we said this was millimeters up here, then that's how that would work. All right, now that we know the height, we would just have to figure out the radius. But the radius squared is equal to the height squared divided by 2. So I just need to do that. So the radius squared, I'll kind of squeeze it in over here, is the height squared divided by 2, which would be this 32. I'm just going to do 32 divided by the square root of 3 squared. I don't want to deal with the rationalized one. And I'm going to divide that by 2. Okay. That would be 1024, of course, divided by 3. And then we're dividing it by 2, which is really timesing it by a half, right? So it's going to become 1024 over 6. And that's r squared. So r, I gotta squeeze this in here, is the square root of 1024 over 6, which would be 32 over the square root of 6, which is fine. Or that would be 32 square root of 6 over 6, which would reduce because 2 goes into both of those. So it becomes 16 square root of 6 over 3. And again, that would be millimeters if we had millimeters given to us as a unit to begin with. And that's a 6 right there. Sorry, I'm running out of space down here. Millimeters. There, I rewrote it a little cleaner. All right, so that worked out really well, and the math was not particularly difficult, which we really like. That's the advantage of the Lagrange multiplier method.